Moayeri of the National Institute of Standards and Technology in Test and Evaluation of Localization and Tracking Systems.
Thank you. I am with the Advanced Network Technologies Division at NIST in Gaithersburg, Maryland, and we do basic and applied research in networking, and in this case, sensor networks, localization, and things like that. Kirk and Steve did a good job of talking about I would call technology standards, but there are other types of standards. You could have standards for conformance testing. You can have standards for even interoperability testing. In this case today, I'll be talking about standards for test and evaluation of localization and tracking systems. I believe that lack of standardized test and evaluation procedures has been an impediment to market growth for localization and tracking systems because users are typically unable to verify whether a system meets the requirements or not. And this is particularly true for what in the government we call mission-critical applications, typically life and death issues. This is based on working with different user communities and stakeholders for emergency responders in military applications, track miners. So it is quite important because people have been using reporting test and evaluation results using different criteria and procedures, and that has not been very helpful. It is wasteful when you test a system at different places using different procedures, and some results are reported, and it really confuses people, and that has been a problem. So one aspect is test and evaluation procedures. The other is minimum performance requirements. And there have been cases that the minimum performance requirements have been different in different jurisdictions. One example that I have for you, that there was a 2006 Miner Act in the US for use of communications and tracking equipment in underground mines. And now different states have come up with different numbers, that the system has to meet this. If you want to operate equipment for mines in Pennsylvania, it's going to be different from what's in West Virginia. Of course, that is not good for the industry because sometimes these are not. May not be a very large market and then you have fragmentation, and you need to have products that would meet this state's requirement and that state's requirement. That would not be so good. So many stakeholders and user communities have expressed a strong desire for development of test and evaluation standards. And that's what I'll be talking about today. There are different ways of looking at localization and tracking systems. The operating environment could be indoor, outdoors, or both. It could be above ground. It could be underwater. I know for most of you in this room, underwater is probably not important, but it's certainly important to DoD. You can talk about, the system could have, in terms of networking and sensor infrastructure in the environment that you go in. It could be available or it could be unavailable. Jalal Mapar talked about this. Sometimes you need a site-specific training. In some applications it's allowed, and sometimes it's not allowed. Again, Jalal talked about that. And there are also this aspect of capabilities of the platform that you have in terms of computation, storage, radio communications capabilities. And you could have simple things such as just RFID tags on your mobile device and have RFID readers in the environment. You could have smartphones. You could have devices with higher capabilities. So, and then there is this aspect of the speed and mobility. Sometimes you're tracking an asset that is not moving, and sometimes it is moving. So you could have a stationary pedestrian speeds, ground vehicular speeds, and higher speeds. And for example, a unmanned aerial vehicle, that would be your fighter jets. And mobility is important because of for example, if you look at inertial navigation systems, that obviously affects the speed and mode of movement, affects the performance of the system. So test and evaluation procedures may have to be specialized to some extent to the type of localization and tracking system which is being considered. But fortunately, a lot of the performance metrics would be the same. The performance metrics for a lot of it is common. Other speakers throughout the day have talked about this trend of using other sensors for localization. I mean, the title for this workshop is Opportunistic RF Localization, but we could easily drop the RF because the trend is, in many applications, is that RF alone is not enough. And when you think about Apple iPhone and Android, and all of these come up with a bunch of sensors that could be used, and why not? We should take advantage of whatever is available to us. So here you see a list of a bunch of sensors that the DARPA Aspen program, also positioning and navigation, is looking at. They are looking at all these 20 sensors, and they want to have a system that is able to work with any subset of these sensors that is available at any given time. And the subset may change, it may evolve with time, and the system has to be flexible enough to work with any of them, and any subset, and be able to change. Some of these sensors are more important than the other ones. GPS is, of course, or GNSS in general is of course, very important. Any sort of accelerometer and things that you find in an inertial measurement unit, gyroscope and things like that are important. Some sort of a RF ranging is typically important, and sometimes people use altimeters for elevation, measuring the location in the z-axis. So the point of this is that our test and evaluation procedures has to work with systems that may use any combination of sensors. And I'm not talking about the DARPA program alone. So what are the approaches to test and evaluation procedures for localization and tracking systems? Well, there are two types of system types that you can have. You can talk about system testing. Basically, you would look at your testing procedure. You would look at the system as a black box. We don't care what's inside the box. My test and evaluation procedure should work regardless of what's in the box. Because as you can imagine, it's pretty difficult. It doesn't make sense to have one testing and evaluation procedure for this system that has these particular elements in it or sensors in it. There would be too many of those, and there would be a lot of repetition anyway. You can also do component testing. You can decide and go and say, okay, I want to focus on ultra-wideband ranging and go in a lab or in some environment and try to figure out what's the best that can be done with this. Another aspect is repeatability. Sometimes you have one-time site-specific training or testing, not training, testing. That means that you go to a few, maybe one or a few buildings and try a bunch of systems at the same time. And your test and evaluation results are, of course, is really specific to that site that was used. It's very difficult to, repeatability and being able to test in a laboratory is really difficult because lots of times you have to have a network of these devices. There are large distances are involved. How are you going to emulate multi-path fading? How are you going to, deal with mobility, that the person is moving? And when the person is moving, it could be walking, it could be running, it could be crawling, going backwards, and things like that you would see in case of first responders and military personnel, and all of that will affect. So it's very difficult to have a testing procedure that you say, okay, you can do this in California, you can do this in here, and the results are all going to be the same and repeatable. So unfortunately, and this is a pity, one-time site-specific testing is, I do not know how to do system testing in a very repeatable manner that would not depend on the site. So I would say that's the holy grail in testing and evaluation in this area. So one other thing that you can do is modeling and simulation. In case of network modeling and simulation is a very accepted paradigm, and people do modeling and simulation for finding the performance of networks. There is no counterpart to that for localization and tracking systems. So still quite a bit of work needs to be done in order to be able to, for example, generate data the way that a sensor of localization sensor would produce that data. You would need to have models for data fusion filters, whether it's Kalman filtering or particle filter or factor graphs or other methods that people are looking at. And even Kalman filtering has extended Kalman filter, unscented Kalman filter. There's a variety of things that can be used. And of course, whenever you use modeling and simulation, there is the fidelity of the approach that you are taking and the reliability of the simulation results. Those are always issues that are important. And it takes time. It takes quite a bit of time to try to do modeling and simulation. First you have to build your models, and then so that's why there is going to be a standardization activity within ISO IEC JTC1 Subcommittee 31 Working Group 5, which is a group that does real-time locating systems. That's the title of the group. And that has been started already. I have proposed this, and it has passed it's going through the stages of the new project has to be approved before it can the work can begin. It's going through various ballots right now. So the scope of this proposed test and evaluation standard is first we need to develop performance metrics. What are the appropriate performance metrics for test and evaluation test and evaluation scenarios? And I'm just going to give you a few facts about this. Primarily, in the beginning, we are going to focus on localization and tracking in buildings, but we will also consider transitions between indoors and outdoors. Because outdoors, of course, GPS and GNSS is the dominant technology, but some of these systems would like to show location in lat long, even if you go inside a building, and that causes some problems because lat long is not the natural way of showing lower elevation from the ellipsoid is not the natural way of showing location inside a building. And there are problems with even if the person goes into this building, do we know the coordinates of the corners of the building? I mean, if you use Google Map or Google Earth, you really need to have that location up to several digits after the decimal point, because if you use your RF ranging or whatever and you do localization inside, if the corners of the building, even if your GPS is working very well, but the coordinates of the locations that you have for the corners of the building are not good, you're going to have a problem because the two will not be a good registration between the two. So it is going to focus on black box testing. But at the same time, when you do black box testing, you need to be cognizant of the failure modes of various localization and tracking sensors in order to make sure that you are designing a comprehensive test and evaluation scenario. For example, in case of ultra-wideband ranging, that the RF does not penetrate metal, So when you do that, if you have a metal wall, it's going to find the length of a reflected path, and that's of course wrong. If you're looking at magnetometers and things like that, when you go in a building in certain environments, there might be a lot of metal in a computer room or something, and your magnetometer would, in terms of direction, would make a lot of mistakes. If you're looking at accelerometers, if you go and come back to the same place, some of the errors will cancel out. So there are a bunch of you need to make sure that your test and evaluation procedure will include scenarios that would stress all of these sensors, even though we don't want to assume what exactly inside the box. So it's going to be one-time site-specific testing, but we need to test in different buildings. I mean, we have seen this. We have done testing at NIST, because many of these systems typically need radio communications and networking capability to function properly. There is one aspect that who needs the location information? The person who is moving, or sometimes there is an authority that needs that. The incident command in case of firefighters outside of a building, or if you're doing offender tracking, somebody moving around in a city, somebody else needs to know where you are. And that issue of communications, even the mobile knows where he is. That issue of communication from inside the building to outside, as you know, is still an issue. So I already talked about various modes of mobility that needs to be considered. And testing and evaluation procedures for other applications domains, such as miners trapped in underground mines, submersible vehicles like submarines and things like that, or Kaveh talked about, Pahlavan talked about the small medical devices moving around inside the human body. Those are, I regard those as specialized areas that they may be the subject of future extensions to this basis standard. So here are 2 pages of performance metrics for localization and tracking systems. I have tried to sort of put down a few of these as I know right now, but the work hasn't started, so this is a tentative list. Of course, when people come to this standardization committee and start working on this, there may be other performance metrics, or some of this may disappear. So I'm not going to. A lot of it has to do with location accuracy and consistency, and also latency. Latency is also important when you say, give me the location of this. If the system takes like a couple of seconds to give you the location back, well, that may be okay in some applications, but it may not be okay in if you're talking about a precision-guided munition or a fighter jet. That kind of delay is not acceptable. So latency is important. And keep in mind that the location is, who needs the location? The mobile itself, or sometimes somebody else? A tracking authority needs the location, and if there is a delay, if you're trying to communicate and you have packet loss and the packet doesn't get out and you have to do retransmission and things like that, that would cause some problems. So it is not my intention to go over these 2 pages of the performance metrics, but instead I'm just going to show you some sample results for test and evaluation. This is a system that was tested at NIST. And here we are showing that these dots that you see is the horizontal error vector. So there were 100 test points in a building, and with precise locations surveyed so that we had the precise locations of these test points. And at these test points, we asked the system to produce the location estimate. So if you look at the location estimate minus the true location, that would be your error vector. We are looking at the XY coordinate in case of this particular graph in here. So those dots that you see is all the error vectors in those 100 test points. And the significance of the colors is that the test started at some time T mean, ended at time T max. And if you end up and you see that the green, a lot of the large errors are green, then you can say, oh, that corresponds to that segment of the building when the person was moving in that area, and you see and then you may start thinking, how can I make the system better, or what happened over there. So one thing that is used a lot in case of localization is the CE95. So this is the radius of the smallest circle that would enclose 95% of your error vectors. So that the radius in this case was 4 meters and 4 centimeters. So that's one performance metric that people use. And of course, mean and variance, or standard deviation of the magnitude of the error vectors. So this is a way of showing the same results as a function of time. Time is plotted on the horizontal axis. This was a test that took 20 minutes. So the person was moving inside the building, going up and down different floors, and sometimes crawling, sometimes walking, and other modes of mobility. And what we have plotted here is the magnitude of the horizontal error vector. So it's basically it has the same information as the previous plot. So R is the value that 95% of the vectors are below this, which is the same thing as C95. It's the same thing as just another way of showing the same result. The Z-axis is quite important. Lots of times systems have difficulty to tell you are on the 60th floor of a building or 80th floor of a building. I mean, I don't think industry even has gotten to, many of the systems do not work when it comes to that type of thing. In this case, here we are looking at the vertical component of the error vector. So this is Z minus Z hat. Z is the true height, and Z hat is the estimate of the height, and the difference is. So this value of V is chosen in such a way that 95% of the points are between minus V and V, and that's called vertical error 95, and in this case it was 2.386 meters. And you can see in case of this system, many of these errors were negative. You may say, what if I add a DC value to get rid of this bias and have a better V95? Well, keep in mind that this is for a particular building. If the vendor knew there was such a consistent bias, they would have added it too. Finally, I'm going to show you, this is another way of showing some of these test and evaluation results. And keep in mind that I have only talked about one or two, maybe two of these, a couple of these performance metrics, not all of them. So this is a building that was about maybe about 30 meters by 130 meters. It's an office building on the NIST campus. In fact, that's my own office happens to be in this building. It's a 3-story building. And the solid black lines that you see was the course that the mobile took, and you see two red. You see the red dotted, and the red dashed is what the system produced. The system was 2 people were moving in the building, moving around, and then they went to the 2nd floor, the 3rd floor, keep going up and down the floors. In some cases, you see instead of a red line, you see the lines become blue, and that's where they were crawling, because we are also interested in see what happens, how does that affect the performance of the system. Anyway, that's also another way of, the point is that the presentation and visualization of the results is also one component of will be one component of the standard. It will be, talk about that a little bit. What is the best way to show these things? Conclusions. Test and evaluation of localization systems, localization and tracking systems needs careful planning and thinking. That's why there is going to be a standardization activity in this area. There is a clear need for this based on what we have heard from different stakeholders. user communities, some government agencies, and the goal is to make sure that the systems will meet user requirements, and we think this will in turn foster market growth for these systems. And you know, there has been a lot of confusion because people come and say, oh, I have a system that works, you know, I'm going to give you 1 foot accuracy, I'm going to give you 5 centimeter accuracy, and a lot of time these things unfortunately have been unsubstantiated, and there is also this problem of the, you know, they do test the system inside a room, everything is line of sight. Well, that's not the real thing. So that's the whole story. That's the end of my talk. Thank you.